Okay, so thank you, Meilon, for the kind invitation, for the opportunity to represent the... it's always strange because scientists always say, I'm unconventional, I'm not a conservative person, but here I'll be representing the conservative worldview of the main scientific community based on decades of simulations, computations, measurements, and theory, which say that quantum computing is possible and there's no known physics that forbids it, both fundamental and experimental. So that's the bottom line. There it's out there. So we're going to be, I'm going to be a little more, let's say, down to earth than Gil, in the sense that I'll be showing explicit implementations and discussing specific attempts to realize and talking about the actual progress that has been made, mainly in the last decade. There are several models which I'll mention and briefly review to implement quantum information processing. And Gil mainly discussed the gate model, but there are others which are both interesting and potentially fundamentally exciting in their robustness to noise and implementation potential. Now, let's just get started with some motivation. So the famous Schrodinger cat experiment involves placing a cat in a box and coupling a radioactive decay to a distinct unitary process which terminates the cat. After one half-life of the radioactive decay, we have some sort of entangled situation of a decayed atom and a superposed live and dead cat. Such a macroscopic superposition is never observed in everyday life, indicating that maybe Gil is on the right track. But quantum theory, at least, says that this is a perfectly legitimate state. Now, those of us who studied quantum mechanics and those of us who follow the theory know that the interaction or connection of the cat to its box environment and unknown degrees of freedom create a form of what Zurich has coined eigenselection, which defines classical pointer states which are stable to this noise. And therefore, we never see such superpositions. That's the short conventional wisdom answer why classical reality emerges via each part of the universe measuring the other part and localizing it in these classically stable states. So Aristotle said that nature abhors a vacuum, and Schrodinger said that nature abhors coherence. And that's something which we have to understand, those of us who are attempting to process quantum information. Nature is a devious and controlling mistress who attempts to measure our quantum information and sneak into our lab and steal our expensively bought coherence. Now, this is related dually to a problem that Feynman noted already in the 80s, that there's appears to be an exponential computational overhead for simulating interesting many-body systems. This includes high-energy processes, but also simpler, more mundane systems like molecules and even atoms, if you start including higher-order relativistic corrections, in order to really get the energy levels of even a simple multi-electron atom. You have to start working harder and harder with your classical simulations. More memory and more simulation times just to understand a very, very simple system. Of course, you can make some approximations, mean field, etc., which take you to a certain precision, but when you want to go higher, you have to include degrees of freedom, fluctuations, and it just grows larger as you demand more precision and finer tuning of your understanding. So Feynman noted this. Of course, in many body systems, we have the exciting possibility of engineering materials if we could just understand better how the known interactions lead to emergent properties. So known spin properties of molecules and unit cells, when you place them in interaction, there's no known way to compute the many-body magnetism, a ferroelectric transition, high-temperature superconducting transition, even though the individual constituents are relatively well understood. Everyone knows, to sufficient precision, we think, what the atoms do. We know what the electrons, which are in the single particle band structure, are doing. But the collective effects with the interactions are not understood. And this requires, if you just plug it into a computer, exponential overhead in order to even come close to simulating. And of course, because it's exponential, that's a really rough switch. When you start going from 10 to 20 to 30 particles, you're dead. Even the strongest supercomputer cannot compute these systems reliably. And subsequently, at the level of hundreds of particles where these systems are exciting, are not reachable with current understanding and numerical methods. So quantum information processing says, okay, maybe if we were able to somehow engineer a quantum system which were sufficiently isolated, sufficiently controlled, and sufficiently measurable so we can look at the internal correlations and learn more about what's going on, maybe we can get a practical advantage over classical information processing related to, say, these many-body system simulations. And there are many exciting connections, as Gil started mentioning, to quantum phase transition and computational complexity, emerging almost mathematically from these effects. And from the experimental perspective, yes, Onan?
Nadav, I have a question. Do you imply that, okay, we all agree, I guess, well,
I haven't implied anything. I'm just trying to motivate myself.
Yeah. Also, Scott said in his talk, and people say that for me, that the best quantum simulator of a system is the system itself.
No, that's not what I'm saying.
The system is also coupled. Even any system that you would want to engineer to understand the many bodies.
Okay, let me explain.
It's part of the thing.
Let me explain.
Let me just refine the question.
Okay.
And so my question is, do you imply that it's easier to build a universal quantum simulator that will allow you to tweak all the parameters to really understand the physics than to build the systems themselves or many systems and check them out? And tweaking the parameters experimentally on different systems, so you think it will be easier to build a universal quantum?
That's not what I said. That's not what I said. I think special purpose quantum simulators can give us a lot of insight because we know the Hamiltonian. That's what a simulator is. You put in something known, you can switch on interactions in a more controlled way. Whereas a system which can be doing something very, very exciting often has an unknown Hamiltonian. And also often, especially, for example, the typical example is high temperature superconductivity. We can measure this macroscopic property of superconductivity, but we don't have experimental probes to measure many of the exciting correlations which are occurring within this material. So we can theorize about it, and we can measure macroscopic coarse emergent properties, but we never get a final answer of what's going on, even after 20 years of intensive research. So it's still an open problem, which is, of course, exciting. Now, so I'm saying, suppose I wanted to simulate high temperature superconductivity. So I would start out with a system which is sufficiently simple and understandable, and then switch on the interactions and observe if that is enough to get high temperature superconductivity, because it's a known Hamiltonian. In addition, in such a system, if it were properly engineered, I can measure, because it's a simulator, I can measure correlations which are inaccessible for the system I'm trying to model. And then subsequently, you can experiment on this system and learn what is the minimal model for high temperature superconductivity, which actually emerges from a quantum evolution.
Yeah, but my question
so the bottom line is, we've tried to do the approach you suggested, just measure different high temperature superconductors. We've learned a lot, but not enough. So this is an additional approach. Let's build a special purpose, and I think I'm going to continue, and we'll discuss it later. This is the first slide,
okay,
and I agree it's exciting, and there's a lot of questions, but unless it's something short, maybe we'll continue, with your permission. Sorry. Okay, so the experimental challenge is, this is something very, very deep. It talks about what makes our everyday classical, what generates the arrow of time, the subjective arrow of time, whereas in quantum mechanics time is reversible. And these are questions opening up is, how big and how isolatable a Schrödinger kitten can we make? And for experimentalists, this is like a gauntlet which is tossed down there. We want to try. We want to see how high and how far we can go. Okay, so maybe this will help resolve some things that you wanted to discuss. So I figured I'm going to take an Aronson approach. I'm just going to put out here my main conclusion or comments, things which sort of burst the bubble on popularized quantum computing. It's not infinitely more powerful than digital computers for any application. It's very, very specialized. So let's start out. It's mainstream physics and computer science to consider it possible with established error correction code to build quantum computers. This is a mainstream understanding of physics and computer science today, since we have never measured noise models which concur with what Gil suggests. Although that doesn't mean they may not be possible on a more refined level. But on the first approximation of all the work we've done, we have not observed these malicious correlated errors to exist. And that goes into the assumption of error correcting codes, quantum error correction codes, and makes quantum computation stable once you reach a certain fidelity. Okay, here's an important point. Quantum computing is not analog computing. Analog computing is what is attempted, for example, when you do a soap bubble simulation, or when you try to build a billiard ball system and launch one along a trajectory which bangs into all the other balls and then tries to do some sort of computation. That's an analog simulator or emulator, and that is inherently unstable to noise and chaoticity. That's why digital computing has really swallowed analog computing. Digital computing is naturally error correcting because it has a threshold. So any noise which it occurs is cut off by the digital computing, and this is done all the time. So it doesn't let errors propagate internally within its basic building block. However, quantum computing, by virtue of being a hybrid of analog and digital reality, in a sense, I'm going to annoy Chagai now, by saying that the particle-wave duality of quantum mechanics actually means that quantum mechanics is simultaneously digital and analog. And it's right on the border of being sufficiently digital to allow error correction to work. Because when you do a measurement, you get according to the von Neumann postulates and what we observe in the lab, you get a digital collapse into particular eigenstates. Whereas the evolution of the amplitudes is continuous and analog-like, the collapse is digital. And that's enough. That's what was proven by Miki and DeWitt and others years ago. And it's not always completely understood. People look at this analog, all these 2 to the n amplitudes, and say, oh no, you have so many amplitudes and they're all going to be so sensitive, it's never going to work. That's not true. Error correction, when it applies, can overcome this. Now, once again, failure of quantum computing, which is what Gil indicated, actually, in my opinion, implies fundamentally new physics regarding decoherence, like spontaneous collapse models beyond what we've ever measured. Some sort of, maybe there's all kinds of exciting theories, but none of them have ever been measured, like gravity waves creating some sort of correlated dephasing. all kinds of exciting ideas, but none of it has ever been measured. Maybe our research will be on the way to see these effects if they exist.
But this is not related to what I say.
Okay, but in general, a failure of quantum computing within the known paradigm of decoherence and noise, in my opinion, would imply fundamentally new physics. We can discuss it later. I think you would need a new error model to cause the failure of quantum computing. Now, once again, quantum computing is not magic. General and generic unitary evolution of a many-body state is still exponentially hard to simulate within the quantum computing model. So if you want to do some general, crazy interaction, long range, whatever, it's going to take you generically, on average, it's an exponentially hard problem within quantum computing. However, if you have some exciting symmetry, which often we do in Hamiltonian and maybe even in a structured algorithmic problem, then you can, if you're clever, make some sort of do tricks with the interference and achieve some sort of exciting speed up or calculate something useful. Okay, so this is kind of standard slides. Classical bits are digital states of a transistor or some sort of mechanical, classical, electrical system, which can either be on or off. Quantum bits can be in superpositions, and when we talk about superpositions, we're talking about, for example, states in an atomic system, which are known to the audience. Some of the people here actually taught me these things when I was an undergrad. Now, a geometrical picture for a two-level system is often given by the Bloch sphere using the familiar mapping of a two-level two-level state in Hilbert space can map to a three-dimensional sphere in just orthogonal real space. So the state of the qubit is actually here given parametrized with a 0 and 1 eigenstates by these amplitudes with an angle theta and another angle phi, just placing us somewhere on the sphere. And the north pole is the 0 state, the south pole the 1 state. Anything on the equator is an equal superposition with a particular phase. Now control is some resonant pulse or some sort of wave plate which rotates these vectors around. That's a single qubit control, can be done with extremely high fidelity. I'll show you numbers as the talk progresses. Now, experimentally, we need to characterize our qubits, so we do all kinds of rotations and lifetime measurements and phase coherence measurements and maybe echo measurements, and this is already data which is close to a decade old, showing a particular qubit, a superconducting qubit. This is data I took myself, showing a particular lifetime, particular dephasing time, not particularly good, far from what is achieved today, but the idea is you need to benchmark your qubits and then define how good they are relative to the thresholds, relative to some general integration program. Now, we said integration, so what is the paradigm of the gate model, for example? Let's take a bunch of qubits and talk about their combined state. So combined state of this tensor product Hilbert space has 2 to the n with n qubits, complex numbers needed to specify a general n qubit state. Actually, it's 2 to the n minus 1 because we normalize the state vector, but that's already enough parameters to make most people happy. Notably, many, and actually most, as n becomes larger, it becomes just unity, of all these states are entangled in the sense that they cannot be written as separable states of individual qubits, but they need to be discussed as a correlated state. That's generic as you go to larger and larger Hilbert space. The volume of the entangled space just dominates everything. So a classic 2-qubit example is the Bell state, in which we have this sort of anti-correlation. So the first digit is the first qubit, the second is the second qubit, and we see here that if, for example, I measure the first qubit to be 0, then I know the second qubit is 1, and vice versa. This state is actually more subtle than just having, for example, let's check, oh, my socks are the same color, So suppose I were confused and I wore white socks and black socks. It's called Bartleman's socks, this paradigm. So that's not the Bell state. The Bell state is actually more subtle. It's immune to rotations in the sense that they're always anti-correlated no matter what basis you measure in. And Bell violations turn out to be extremely useful as resources in quantum secure communication. This implementation actually is already in the field. You can buy a secure quantum communication system and carry over fiber over tens of kilometers, quantum entanglement, sufficiently secure to communicate
Theoretical
codes.
explanation uses entanglement.
What's that?
They don't have entanglement.
No, they use weak photons.
Only the theory for proving security uses entanglement.
That's true. That's true. They use weak photons, but still, the security is determined by the fact that it's well, it's not entangled because.
The point is about the applications.
Yeah.
Not in principle, because there were demonstrations
Yeah.
of that protocol as well. But
Yeah.
the applications don't use it.
Okay, so that's I appreciate the correction. The products you can buy do not rely directly on entanglement, although they do need it to prove their security. However, in the lab, people have demonstrated fully entangled communication, which is secure to a certain extent within their fidelities. Now, so in order to generate these anti or correlation states, you need some sort of interaction because, as we said, normally each qubit was just starting out on its own. So to build up such correlations, you need to do gates. And this is sort of a comparison. It's called the De Vincenzo scheme of the gate model. And so this classical computing, you start out with, you have to be able to initialize your state. Sometimes people forget that, but in both these paradigms, you have to be able to initialize your state sufficiently well. It's not an obvious thing. Maybe there are issues of not being at zero temperature. Gil has been studying that. These are, of course, important questions, but still, error correction says we can overcome that if it's only good enough. It doesn't have to be perfect. So, classical logic means for a classical computation, you need to be able to do a not and and. Actually, there are several other ways of building up a universal classical gate, and actually, it turns out that it's almost hard to avoid universality in a certain sense, also in the quantum states. So you just churn through a bunch of gates on a bunch of initial qubits according to your algorithm, and finally, you output your result. If you have errors, then it's possible to do error correction, but in many cases the current hardware is sufficiently good that error correction is rarely used. Error correction in classical computation is used very aggressively in communication, which is often noisy, but less for the actual computation, which has become extremely reliable due to transistor technology. There are some bit parity checks on memory because, again, flash memory is not as reliable as the older memories, but still, the main computational it could require error correction if you want to be truly indefinite, but often not critical. Quantum computing is quite similar in its sort of layout here in this gate model paradigm, and here we have initialize, you want to be able to manipulate your single qubit gate, controlled 2-qubit gate, some sort of evolution. For example, here you start out with particular basis state of the 2-qubit state, and you want to be able, under the 2-qubit gate, to evolve in this particular way. And any superpositions of these should evolve in a linear combination of these control gates. And finally, you'd like to measure. Now, of course, interleaved within this, you need to be doing some sort of clever error correction, otherwise it'll fail. And if your coherence time over your logic gate time turns out is larger than 100, meaning you can do 100 operations within your coherence time, then the most advanced protocols for quantum error correction, under the assumptions of uncorrelated noise, give you the ability to build up logical qubits which are more and more robust to these local noises and eventually give you sufficient fault tolerance to achieve your computation. With a polynomial overhead in corrected qubits, you can build up an arbitrarily long computation. So you need to be clever because most of the algorithms will generate nothing. You'll just try out of your 2 to the n amplitudes and you'll measure something useless. So in order to do something interesting for the quantum computer scientists, then you have to be clever and engineer the interferences of your phases such that when you measure, the probability of finding something interesting is higher. And these are some famous algorithms. Shor is well known. I don't know if the E should be there. Grover's algorithm is for an unstructured problem, and it gives you a square root of enhancement, but it doesn't bring you back from exponential into polynomial. So it's only polynomially faster, not exponentially faster. These are the famous and well-quoted ones, but there are some other problems which are maybe more interesting to a physics audience, such as quantum random walks, boson sampling, hidden subgroups, eigenvalue estimation. These are problems which physicists can connect to maybe more naturally than these number theory sort of connections. Okay. Now let's start talking about the implementations. I have 20 minutes, and that should be enough to show you that we've come a long way. So about in the year 2000, qubit lifetime, this is from a review, it's already a year and a half old and things have gotten better since. You can see a very dramatic exponential increase. This is time in years, starting from say 98, 99 and going out to 2013 when this paper was written. And you can see the increase in qubit lifetime. Here it's in nanosecond, going from 1 nanosecond to an order of 100,000 nanoseconds in 13 years. So this is a progress which is faster than Moore's law. And there's still more work to be done, but things are progressively getting better and better for these qubits. But that's just an example. Other systems, such as ion traps, have also been doing quite well. So I mentioned alternative computational models, and this is a very interesting connection here.
Can you tell us how that first advanced? What was the basic idea?
Which one? The first qubit?
Yeah. No,
all the slopes? Every single one of them was a minor breakthrough. It involved understanding the environment and engineering the noise and engineering the system and various parameters, and every single one of them was a small breakthrough. Both fundamental science and engineering together. Yes, One.
According to your graph there, you're at least 1 order of magnitude over the limit for error correction?
Correct. Correct. The system has achieved, already a year ago, has passed on all parameters, including 2 qubit gates, measurement, everything, and all parameters it has passed the surface code fault tolerant threshold. And I'll show more about that. Okay, so alternative computational models. These are very exciting ideas to implement something which initially looks very different from the gate model. So for example, cluster states, it's the idea you generate via strong interactions at the beginning. You generate a massively parallel entangled state. Typically, this is discussed in the context of photons, optical photons. So you generate, this is a representation of entanglement. Every bond here represents an entangling connection between different photons. So there's a whole subfield discussing these cluster states and their symmetries and how to build them up and what are the mappings from one to another and how to experimentally generate them. But these massively entangled states, once they're prepared, you can prune by measurement and feed forward on the result of the measurement. You can prune the graph down, and subsequently by just measuring and doing measurements which depend on the result of previous measurements, but everything classical, you can eventually run your computation on this initial state. So you have to start out with some big entangled state, but then you just measure it through. Another very, very exciting idea, which Chagai is working, I think, on experiments related to both these concepts and computational models, is the famous KLM paper, in which you go even simpler. You don't even have to start out with this massive entanglement, which seems intimidating to produce. All you have to do is start out with a linear optical network, beam splitters and modes. And phase shifters. Beam splitters and phase shifters. Very linear optics, very standard optics, very high fidelity optics, which can be bought off the shelf. And all you have to do is be able to produce on-demand single photons. So if you have a photon machine gun, something which you press a button and emits a single photon, you can send those into this network, linear optical network, and achieve with measurement and feedback on the measurement, and achieve universal quantum computing. Of course, this is a very subtle and beautiful protocol, and some exciting steps have already been taken towards implementing it, including here at the Hebrew University.
Because you named me, the second approach was in principle just a proof of concept. I don't think anyone is really trying to build exactly that because it's very inefficient.
Yes, yes, it's very.
So I think it was the first time that photons were shown to be useful for quantum computation. But nowadays, I don't think the second scheme, I'm talking about the second one, is something that is regarded as applicable.
Yes, and the main issues are, for this particular implementation, if you already mentioned the experimental difficulties to the next order, this implementation it's very difficult to error correct it without large overheads within the current experimental capabilities. So if, for example, you were able to introduce a small but controllable nonlinearity which would cause the photons to interact, things would be much better for this implementation. Now, the adiabatic algorithm is another exciting idea in which you start out, for example, here this is time, and these are the eigenenergies of a particular Hamiltonian. And what you're doing is you're just slowly changing the Hamiltonian from a trivial one to the many-body one you want to know the ground state of. And if you do it sufficiently slowly, the idea is you would stay in the ground state and eventually end up in an exciting many-body ground state you can measure. And the adiabatic algorithm was proven by Dorit and Aronov and others to be equivalent computationally to the gate model. Yes?
There was something that was said yesterday. I got a bit confused because it was shown initially that, the claim is that a quantum computer would not be able to solve NP-complete problems. But then there is a claim that if you have an adiabatic...
It can solve them, but as exponentially slowly as classical ones do.
Okay, so it's not going to be efficiently solving.
Only conjecture, maybe an analysis.
No, this has been debunked. It doesn't solve them. You know, these are asymptotic and average questions. If you have a particular NP complete problem, you might be able, with a particular computation, to get the solution quickly. But computer scientists talk about the average problem or about the worst case.
You can have a mapping. So if
yeah, but that's a particular problem. Just a second. A particular problem you might be able to solve quickly, but the average problem not. It's not the same thing.
Let us discuss now.
Yes. Okay, topological quantum computing is also an interesting and exciting idea, but however, it doesn't have any experimental implementation yet, so I'm going to postpone that unless you ask me about it. People have proposed it as a beautiful theoretical paradigm, hasn't been experimentally observed yet to be robust or useful towards quantum information. So I'm going to leave that aside, even though it's an interesting experimental system. So if you walk into some of the labs here at the Hebrew University, or just labs in leading universities around the world, you'll see all kinds of systems, and you'll hear excited experimentalists telling you, here, look at this is my ion trap, and I have a chain of 14 ions all entangled doing something exciting, and this is eventually going to be useful towards quantum computing. And here you see some sort of superconducting qubit sitting in a dilution fridge at 20 millikelvin, and also microwave measurements, optical photons, maybe some NMR systems, quantum dots. I don't have an NV center here, but I should. And some single atoms, all kinds of interesting implementations, which, yeah, optical lattices of neutral atoms. All these implementations are quoted as being relevant to quantum information processing, and there are others. And it's kind of like a messy sort of situation. How should we view this? So maybe we should have a guide to the perplexed. The idea is maybe looking at the individual qubits, starting from photons, which are the least matter-like qubit. They're excellent single qubits, but their coupling is hard because they're so immune to decoherence. And they're immune to decoherence because they don't interact very strongly with matter unless they fully scatter off of it. But in general, they don't interact with each other hardly unless you really force their hand via some sort of matter coupling. And going all the way out to superconducting circuits, which are large, macroscopical, easily coupled, but the single qubit was a challenge, and we saw that the single qubit coherence times went up rapidly, but that was after a lot of work and not at all obvious. So here, for example, you have very natural quantum system, and here there are more artificial quantum systems that you need to engineer, understand their noise, study the physics at various hierarchies of its implementation. So here coupling is more natural. Here the single qubit is naturally better. So this is sort of, these are the trade-offs of the field, which eventually boil down to something very quantitative. How good are you? Are you good enough? And you want to reach the fault-tolerant threshold on all parameters. Single qubit, two qubit, state preparation, state measurement, measurement feed forward. All these fidelities have to be higher than 99% for the surface code to work, which is the best known error correction code. So some recent results, because my time is growing short. I only have like 8 or 9 minutes in my opinion. So maybe Chagai will correct me if there's something. These are just sort of like just random results, but showing the relative state of the art. These are 8 photon cluster states generated in the Jean-Louis Pan group. So here you see sort of coincidence measurements demonstrating the fact that many of the peaks are suppressed here, and these peaks are highly ordered and close to what they expect theoretically. Then that indicates that they really prepared some 8 photon cluster state. I'm not going to go into the details because I don't understand them fully myself, and Chagai would have to elaborate. But the idea, again, is that that is the level of entanglement that is being achieved in the lab. You can think that's a lot or think that that's pathetically small, depending on your perspective. Ions, for many years, were sort of the leading or singular leaders of the field, and to a certain extent they still are. Their fidelities, so here, the single qubit fidelity of hero ions is way out there at the 10⁻⁶ level on certain cases. For clock transition, single ion, isolated completely from the entire universe at a magic magnetic field to 4th order Zeeman insensitive, etc. Then
gets you 99 points.
What?
So the same angle gets you for 2 qubit gate.
Yeah, so this value is a combined fidelity for both the 1 and 2 qubit gate. And that's already good enough, again, for fault tolerance, sorry. And here's like an error budget in which you can sort of, if you can read that, you can show that they're looking at Raman photon scattering, motional heating and dephasing, Raman beam intensity systematic errors, off-resonant excitation, all kinds of technical stuff. because ion traps are very, very ideal qubits. And all the problems that they've ever encountered out to 5 and 6 and 7 digits are technical. Ion traps are potentially amazing quantum computers. The issues that they've been dealing with over the past 10 years have been technical. There is what I'm stressing in my debate with Gil, that there's no known fundamental barrier, and there's been steady progress. Every 3-4 years, another digit. And the leading groups are Rainer Blatt and Dave Wineland, who recently won the Nobel Prize for his more basic research on clocks and control of single quantum systems, but also towards this quantum information ideas. And the numbers are somewhere around 14 to 6. And actually, recently I heard about a 30-ion experiment which generated a lot of interest, but I'm not sure it's been published yet.
Who did it?
The Blatt group, a 30-ion group, a 30-ion experiment.
Is that configuration or?
Yeah, it's in a linear configuration, but it's always linear. Those are the best ones, I think.
No, they're trying to do like double linear.
They get a lot more noise and heating, technical stuff, when they try to do that. Again, we have some grad students here who know more about it than I do, and they can. I'm happy to be corrected if I'm wrong, but the linear traps seem to show the best fidelities. And actually, you can engineer effective next nearest neighbor and nearest neighbor, etc. connections just like you do in NMR by sort of dynamical averaging. You can actually link various parts of the chain and build up more complex Hamiltonians than just the trivial nearest neighbor one. OK, so atomic systems, beautiful experiments. In my view, these are more demonstration experiments. The control is not yet good enough to really say I'm really doing some sort of true quantum computing. There have been very suggestive experiments looking at fermionic superconductivity, and it's a very exciting field, but they don't really have numbers in terms of fidelities and stuff you can talk about versus the sort of cold quantum computing model that says, okay, where's your fidelity? How good are you? So they're more in the analog emulator sort of stage where it's difficult to gauge how pure their states are, etc. There's some attempts to really clean up the physics and make the experiment more reproducible, but it's very, very difficult with neutral atoms. I spent a whole doctorate doing it, and I think this is more on the side of just doing many body physics experiments and not necessarily building a quantum computer. So it's relevant, and maybe with more control things can be done, but right now I think it's not there yet in that numeric sense. So again, there's some topological work which is going on also here in Israel, and very interesting interferometric measurements, non-trivial Hall states which may have relevant topological ordering, which would make them useful for doing some quantum information processing. But this is, again, something which is in progress. So this is, again, a progress report. It's not a one-to-one. Not every implementation here is at the same level. Just something that has a lot of potential, in my opinion. So now we come to my my personal brand of poison for one of the implementations which I think is quite close, and as Ronen mentioned, has achieved fault tolerance on all parameters. So superconductors have recently, in the Martinez group, but also the guys at Yale have done some beautiful things, and also at ETH and other places. So the surface code fault tolerant threshold has been demonstrated. Again, this is single qubit benchmarking. What they do is, it's called randomized benchmarking. You repeat a set of gates hundreds of times, and that allows you, via fitting the decay, to understand what a single gate, how good a single gate is. Because if you just try to measure one, then it's very, very difficult to get the fine tuning. So if you have a small error, You just repeat the process many, many times, and then it's amplified so you can actually observe it. So the errors are so tiny that just doing a single gate, it looks effectively perfect. And you have to repeat it hundreds of times in order to get this decay here, indicating that the fidelities here that we have are in the fourth digit. So it's 99.9 something on the various. These are single qubit experiments. Here's the 2-qubit experiment with fidelity of 99.4. So the 2-qubit gate is 10 times worse than the single qubit, but it's also, again, within the fault-tolerant threshold. And this is already a year and a half old. Things have gotten better since. This is a 5-qubit sample. Here you can actually see what it looks like. From here to here is 6 millimeters. These are readout resonators, the actual qubits, control electronics, and this is what it looks like. Very recent result, something I think Gil will be excited to hear. And I actually, this is something from December 2014, right before they went into their winter break. So the idea is to take 9 qubits in a chain now and try to implement a baby surface code. So it's not really a surface, it's a chain, but you define your x and z you have a measure qubit and a data qubit, and they're entangled locally next to each other, and you apply something similar to the surface code protocol. And what the main point is why I'm showing this is because they observed their ability to protect against error substantially better than the single qubit. And this is on demand without post-selection. So the improvement is an order of magnitude after they went to, so you start from 2.7 for 5 qubits and 8.5 for 9 qubits after 8 cycles. And so this is the important thing. So this violates your conjecture 1.4. Well, it depends on how you define substantially, but it goes towards that. Now, superconducting implementations, which I'm advocating here, are also exciting, again, for direct quantum emulation, not just these digital sort of things Martinez is doing. You can actually talk about exciting quantum optics, electrodynamics going on in the Hamiltonian directly and measure effects in quantum optics which were unobservable, including work in our lab here. So I have to stick my own slide, my own work here. Alicia's recent publication is an example of that. Another important front for quantum information processing is hybrid systems, where 2 distinctly different quantum systems are matched. For example, these semiconductor systems are matched to photonics outcouplings, and these are, so here I'm showing sort of preliminary experiments, but Ronen, for example, is on the forefront of doing similar single photon source experiments, and with very exciting results recently. Also, coupling, we heard at our colloquium a few weeks ago, coupling single photons to whispering gallery modes in resonators. It was done years ago, but also now here in Israel as well. Another very important front for the quantum information community is these nanomechanical coupled hybrid systems, where the idea is to actually make mechanical Schrödinger-Katz states. And these, again, are more fundamental quantum optics tests looking into possible decoherence mechanisms which are gravity related. So these are matter systems where you're trying to create a true displaced mechanical Schrödinger-Katz state and seeing if you get any enhanced decoherence from maybe gravity related or extremely sensitive processes. And the forces and the sensitivities of these systems are at fantastic. They're inventing all kinds of new Greek prefixes like yokto and zepto to explain how small the forces that they're sensitive to, the noises that they're sensitive to, various groups worldwide. So I'm going to summarize. My time is up. We have exciting new computational models which are potentially better suited for direct implementations. The experimental control and coherence of the system is steadily growing. We expect exciting advances and we've already observed them now. And I think I want to stress, there is no known physics limiting us. We have to learn a lot. We have to solve many engineering problems. We have to learn specific, exciting physics of the systems we're working on. But there is no known fundamental limit within existing physics to prevent these things from occurring. It doesn't violate any law of thermodynamics. It's completely legitimate, and it needs to be attempted with due seriousness because of the remarkable consequences we already discussed. So, thank you again.
Questions? How many qubits now are available in laboratory, and how many qubits one needs in order to proclaim, I have one fast, very primitive computer? Of course not commercial, but from what number of qubits you can proclaim that it is some sort of computer?
Okay, so that depends on what degree of universality you want. If you want a full universal computer, as I think everyone agrees, this is still far, but not infinitely far. If you're willing to settle for a quantum simulator emulator, many-body system which you control and you can measure every single observable in that particular, so for example, an Ising chain of ions. So the best available experiment to my knowledge is over 20 and possibly close to 30. Hasn't been published yet in the Rayner-Block group.
Qubits.
Qubits, yes. And they have measured many-body quasi-particle percolation inside these Ising spins where they can engineer the Hamiltonian and observed effects which are extremely difficult to simulate. In certain regimes, they can understand it as a quasi-particle, but then when they ramp up parameters, it becomes some sort of density wave, and it's much more difficult to understand what's going on. So this is a classic quantum emulation or analog simulator, which is already quite exciting to the community. Now, I would say simply that on the order of tens of qubits, which we're almost there. So in superconducting qubits, it's 9. In photons, it's 8. But things.
Without error correction.
Yes, these are without error corrections. It's not a full quantum computer, so it's not fault tolerant. But still, I believe that with the current fidelities, we can challenge and surpass classical computing within. Let me make a definite prediction: within 6.5 years.
Okay. Other questions? Temperature, it is not the limit?
No, because you have the ability to feedback and dynamically stabilize it. And temperature just becomes an error, which if the temperature is sufficiently low to start with, then it becomes just an error which you can include in your fidelity. So right now, for example, for the superconducting qubit, the temperature isn't strictly absolute 0. And that gives you a small error, which you can tolerate within error correction.
The highest temperature.
Well, you don't want the highest temperature, you want the lowest. But that you can tolerate? It depends on the fidelity of your system. In general, I would say you want your temperature to be at least a factor of 10. So the e to the minus 10 Boltzmann factor will, you want it to be at least a factor of 10 from your transitions. But that's easily achieved in all the implementations I mentioned. That gives you, again, a preparation error of e to the minus 10, and that's well below all the other fidelities that were not good enough there. So it's another error which you can tolerate via error correction.
Other questions, comments?
I have two questions. One, I think Gil is not very impressed with the one qubit. He's not,
Mm-hmm.
No, I'm impressed.
You're impressed?
One logical qubit.
But how does the noise scale when you add?
In which experiment?
Logical qubits or?
You're talking about, for example, Martinez's experiment. Martinez's experiment is 2 weeks old. It's the first experiment in which the environmental noise has been surpassed by a logical qubit. And it doesn't appear, the Gil's conjecture, at least for this particular system, at the level of 5 or 9 qubits, doesn't appear there doesn't appear to be any correlated noise damaging at that level. So again, since you have to be careful, Gil is a mathematician, so I shouldn't say anything absolute, because physics is an experimental science. And of course, until we've measured something, we never know whether it might appear. So it could be that nature is somehow miraculously correlated and is doing some malicious correlation which will destroy our complicated multi-hierarchical error correction, but it just doesn't seem plausible to me, but it could be possible. So you can't rule it out until you've actually attempted it. So I agree with Gil, we should try.
And the second question is for you.
Any other comments?
Here's a question for me. Go ahead.
You want to speak to each other, or you want to speak to the...
No, he asked a question to Nadav, and now he asked a question to me.
Could you speak a little bit louder?
Louder. Yeah, I wanted to ask if quantum simulations would convince you of the possibility of the thing, or not.
Well, it depends. I think, first of all, the experiment with 8 qubits that suppress the natural noise for some logical qubit, this is certainly very impressive. It's 2 weeks, 2 weeks old, so we have to look at it carefully. I mean, it's not, as I said, even I completely agree that this is very promising. Even if the chance for quantum computer is epsilon, then the stakes are much above 1 over epsilon, maybe 1 over epsilon squared. So certainly we should pursue this direction. Now, and this is also, as Nadav said, this indeed goes against the spirit of my conjectures. But it was 2 weeks ago, so I will update that. But this is certainly promising. What I want to mention is we are now in many times. The single qubits are good enough to study these ideas. And now the time is to put them together, single qubits, boson sampling, and to see what will be the effect of scaling. So here we disagree. I don't think the correlation are malicious or miraculous. They reflect the correlation that you want to create in the system. But we will see. About simulation, I think everything, if you simulate a system which is efficiently computable, then of course you can simulate. One quantum system can simulate. No, there is a famous joke about the guy who wanted to sell his dog. And he told his friend that he wanted to sell his dog, and they asked him, how much money do you want? And he said, I want $1 million. So they were a little bit skeptical, but said, okay, good luck. And after a few days, they met him and said, did you sell his dog? He said, yes, I sold it. Did you get $1 million for it? He said, yeah, pretty much, more or less. I got 2 kittens for $500,000. So to simulate one system with another system, of course, both of them, I expect both of them to represent efficient computation, because all the systems we know in nature don't involve quantum fault tolerance. So without quantum fault tolerance, nobody knows to get some supremacy. And therefore this is of course very impressive to simulate one system with another system.
Any others?
Just a question of what happens. One of the good suggestions for implementing large-scale systems is to have either, say, an ion trap, which is very good, and then to connect them somehow by getting the quantum state, say, as a photon, moving it to another one, and absorbing it at the other place.
Distributed.
Distributed. What's called distributed quantum computing. Any attempt or results on experimentation with that?
Yeah, I'm sorry. I should have mentioned that it's a whole field of study called quantum repeaters, which is very active. It's actually one of there are several projects here at the Hebrew University related, including my student Rafi is working on similar concepts. And the idea again is to distribute your quantum information via teleportation, via communicating over distant channels, and then correlated nodes becomes less and less plausible, and it boils down to the fidelity of your transfer of quantum information. So here it's quite difficult because again it's photons, and photons have to it has to be photons, and anything having to do with photons, you take a hit on the on-demand fidelity. So if you do some post-elections, you have beautiful demonstrations which are remarkably good. But the extraction of individual photons and their absorption with true unit efficiency,
Yeah, so it's not scalable.
it's not there yet. But things are steadily getting better, and so I don't want to say it's not happening, because there are serious projects in this direction, and they've shown steady progress. It all seems to be technical. There's no fundamental reason why you can't absorb and emit photons in a better way. Things are being done at the 90% fidelities for the best systems, but and under certain parameters it can go higher, closer to 99. So it seems technical. So people are working on it.
Okay. I think that both the talks and discussions are very helpful, at least for me. I saw a sort of a battle, and the result are really impressive. So thank you very much, both speakers, and thank you people who managed to come in spite of strong wind. This is a big achievement. So.